Okay, let's see if we are live. Let's check it. Okay, I guess, yeah, we are live. Cool. Okay, so good afternoon, everyone. So we have a nice audience already waiting for the beginning for the talk. So today is another huge pleasure to have another great astronomer and a great inspiration for young astronomers, especially young women. So today we have with us Professor Jocelyn Burnell. And let me put this on the screen so you can see both of us. So welcome, Professor Jocelyn. It's a great pleasure to have you here. We cannot describe how we are happy to have you here. People were really excited before the talk when we were advertising it. So it's a great moment for our institute. And just before we begin, I would like to introduce Professor Jocelyn. So Professor Jocelyn inadvertently discovered pulsars as a graduate student in radio astronomy in Cambridge, opening up a new branch of astrophysics, work recognized by the award of a Nobel Prize to her supervisor. She has subsequently worked in many roles in many branches of astronomy, working part-time while raising a family. And she's now a visiting academic in Oxford and the Chancellor of the University of Dundee, Scotland. She has been the president of the UK's Royal Astronomical Society. In 2008, she became the first female president of the Institute of Physics for the UK and Ireland. And in 2014, the first female president of the Royal Society of Edinburgh. She was one of the small group of women scientists that set up the Athena Swan scheme, and she has received many honors, including a $3 million Breakthrough Prize in 2018. The public appreciation and understanding of science have always been important to her, and she's much in demand as a speaker and a broadcast. So thank you for separating a time for being here with us. And in her spare time, she gardens, listens to choral music, and is active in the Quakers. She has co-edited the anthology of poetry with an astronomical theme, Dark Matter, Poems of Space. Professor Jocelyn, as I said, it's a huge pleasure to have you here with us. Thank you for accepting our invitation, and please feel free to go ahead and talk to us a little bit about pulsars, magnetars, and fast radio bursts.
Thank you very much. I wish I could be with you in person, but the COVID-19 will not allow that. So we will do it by this remote way, and I hope I can be clear. I can't see you, so if you fall asleep, no problem. But if you're looking puzzled, I'm afraid I cannot see it. I'll do my best to be clear. Thank you for the opportunity to talk about this. What I want to say a little bit about is radio astronomy as a branch of astronomy, then talk about pulsars, including a bit about the discovery, and moving on to some other things that have spun out of pulsar work, magnetars and fast radio bursts, both of which are also very exciting. So this is primarily a radio astronomy talk. There will occasionally be reference to X-rays and gamma rays, but primarily radio and quite long wavelength radio astronomy. Radio astronomy started after the Second World War. In Britain, it started at Jodrell Bank, and this lovely photograph shows the big telescope at Jodrell Bank, which is now quite old, but it has been given World Heritage status So the university must continue to keep it standing and maybe also working. I did a little bit of research on radio astronomy in Brazil. I found some information about these telescopes at Itapetinga. The one on the left works at really very high frequency, much higher than I've ever worked. The one on the right is in a frequency band often used by radio astronomers, including those who study pulsars. I moved to Cambridge after doing my bachelor's degree in physics and discovered that it was a place apparently full of very clever people. They were quite keen to let you know that they were clever, I must say. And there were very few women. And I was quite sure they had made a mistake accepting me, that they would discover their mistake and throw me out. Our first day did not help. The new graduate students were given a set of tools each. This is my set of tools. It's about the first tools I ever owned, and I still have them. And you'll see that these are not microelectronics tools. These are standard wire working tools. And I did a lot of wire working, I must say. My job for the first 2 years was to help build the radio telescope that I would subsequently use in my final year. And this is one of the photographs near the end of the construction. My particular job was all the cables, all the connectors. And we have been I have been putting connectors on the ends of some low-loss cables, air-spaced cables, that you could not coil up and take indoors. So I had one end of the cables at the little hut, red and white hut that you can see, and the other end of the cables in the distance where there is another red and white hut. And I worked in that hut through the winter. It was very cold. The connectors are now all on, and we're checking the impedance to make sure that the connections are good. And if anybody's done anything like this, I'm using a slotted waveguide. Working in the field is quite difficult. The nearest power supply is about 400 meters away, and sometimes the connections failed, so it required a lot of patience. The telescope we were building was large, huge, an area like the area of 57 tennis courts. It was not very expensive. We keep quiet about that, just in case everybody thinks astronomy is always cheap. That grant would have bought new houses for 3 newly married couples. 6 of us worked for 2 years to build the radio telescope. And as I said, my role was all the cables, connectors, and transformers. The other 5 people did mostly the heavier work. I was spared most of the sledgehammering, but by the end of my time, I could swing a sledgehammer. I was really quite strong. This is the finished telescope. It looks homemade. It is homemade. There's over 2,000 half-wavelength antennae, wavelength of 81.5 megahertz. Sorry, frequency of 81.5 megahertz. So the wavelength is 3 or 4 meters. There's a lot of copper wire in this telescope. You can perhaps see the bluey-green copper oxide on the outside of the copper wires. There are a lot of wooden posts to keep the wires up out of the wet grass. And those slanting posts carry a reflector. You do not need a solid mirror reflector when you work at these frequencies. Some strands of wire will serve as a very good reflector. And at that time, Cambridge still used vacuum tubes in their receivers, valve receivers. They did ultimately change to transistors, but they delayed quite a long time. The purpose of this radio telescope was to find more quasars. At that time, there were not many quasars known, probably only about 20, and it wasn't a very good sample. We needed more. In amongst everything else, I did find more quasars, about 180 more, so the sample went up from 20 to 200. There was a neat technique for finding the quasars that my supervisor, Tony Hewish, had devised. The top diagram here has quasar, which should be much, much further away, radio waves from the quasar coming down through some clouds to a radio telescope on the surface of the Earth. The clouds are in the solar wind. They're coming off from the sun, blowing off from the sun. And the clouds are actually electron density irregularities. And these electron density irregularities diffract the radio wave. And the radio wave ends up going in several directions after they've been through that layer of cloud in the solar wind. And so the radio telescope picks up a fluctuating signal, because some of the time it's viewing the quasar through one of these electron density clouds, and at other times it's viewing the quasar through gaps in the electron density clouds. And so the intensity received jitters up and down, as you see in the bottom slide. And note the time scale. That little bar at the left of the diagram is 1 second long. So the jittering is quite fast. This is called interplanetary scintillation, because the clouds in the solar wind are in the interplanetary space in the solar system between the planets. And as the radio wave comes to Earth through that bit of space, it passes through these irregularities. A radio galaxy, by contrast, has a much broader angular diameter, and a radio telescope viewing that will see that broad radio galaxy through some of the irregularities and also through some of the gaps at the same time. So the clouds of electron irregularities passing by don't cause the same amount of fluctuation. It's only small angular diameter sources that will fluctuate like this. That is, quasars. So yes, the project was to find more quasars, and we were going to look for this rapid twinkling or scintillation. Interplanetary scintillation is the official name. To detect that scintillation, you must use a short time constant, a short integration time. And I used an observational integration time of 1/10 of a second. But a short time constant makes the signal to noise worse. So you have to build a very large collecting area to get the signal to noise good again, to pick up lots of signal. And that's why the telescope was so big. Having spent 2 years building the telescope, I then was the first person to debug it and observe with it for 6 months. And as I've already said, I found about 180 more quasars. This is 1966-67, and at that time, Cambridge University had 1 computer in the whole university. It was made with vacuum tubes, and it took up a huge room, and it had memory less than your laptop. And very few people could have time on it. Martin Ryle's group did, because they were making maps of the radio sky and they were doing Fourier transforms, Fourier inversions. And doing that by hand is painful. So they had time on it, but nobody else in the radio astronomy group had time on that computer. Our data came out on these long rows of 3-pen chart paper. And you see in the picture some of this chart paper and myself analyzing it. There was 30 meters of that chart paper every day. We took 4 days to do a complete scan of the sky. So that's 120 meters of paper per sky scan. And I observed for 6 months. So I had over 5 kilometers of that paper. It was a lot. I quickly got used to identifying the twinkling quasars. I also got used to identifying man-made interference, because a big radio telescope like that will pick up every radio wave there is from Earth and from space. And at that time, cars, automobiles, were rather badly suppressed, and you could get radio waves generated by the sparks. An arc welder would generate radio waves. A sparking thermostat would generate radio waves. If they were on our band, taxi radios, aircraft altimeters, all these things produce radio waves. There are several bands that are meant to be kept clear for radio astronomy, because even a small terrestrial signal will swamp the cosmic signal. But it's not always respected. Pirate radio stations sometimes used our radio astronomy bands. So anyway, I got used to identifying the quasars, and I got used to identifying this interference. But there was just occasionally another signal that didn't look like a quasar and didn't look like interference. And this little bit of chart shows the first example of that signal. The data has been through a high pass filter. So the center line is quite straight. And on top of that, you can see receiver noise. You can see a bit of low level interference. That really is low level interference. And you can see what turned out to be the first pulsar. And if you look at those two, the pulsar and the interference, they look a little different. For instance, with the interference, you can see space between the spikes. Whereas on the pulsar one, particularly at the left-hand edge of it, the spikes are jammed so close together, you don't see any paper between them. And the interference signal goes up and down, whereas the pulsar one largely goes up with almost no down, maybe just a little bit of overshoot. Incidentally, when you make that kind of comparison, you are actually doing a Fourier analysis. When you say that there's space between the spikes on the interference one, you're saying that it's got lower frequencies in it, whereas the pulsar one has higher frequencies. And when you say on the interference one, the spikes go down as well as up, you're talking about the amplitudes that are observed. So when you look at this kind of thing and say they're the same or they're different, you are actually doing Fourier analysis in your head. Not with the full mathematical quantitative, but the essence of Fourier analysis. Now, the first time I saw this peculiar pulsar signal, I marked it with a question mark and passed on. I had many more meters of chart to analyze and I couldn't hang around. But at some level, it registered, because after a while, when I saw one of these signals again, my brain said, "You've seen something like this before, haven't you? You've seen something like this before from this bit of the sky, haven't you?" And then it's easy, because I store these rolls of chart paper by the declination we're observing. And they're stored in shoeboxes with the declination marked on the end of the shoebox. So you go find the shoebox that covers this declination strip, get out all the old charts, get a large clear space. That was no problem. All the graduate students were housed in an attic, and there was plenty of space to lay out the charts. So you lay out the charts and line them up with right ascension, and you can see the quasars coming back on each chart. The interference, of course, doesn't repeat on the chart, but this signal, when it was present, was always at the same right ascension. It was only there perhaps a quarter of the time, but when it was there, it was at the same right ascension. So my intuition that I had seen this before from this bit of sky was absolutely right. It was coming from a fixed part of the sky. It didn't occupy a lot of the chart. I estimate that it's about 10 parts in a million of the chart paper that this signal occupied. But because we're trained to spot problems and issues and resolve problems and issues, it's the kind of thing that sticks in your mind, albeit maybe right at the back of your mind. Now, sorry, I'll go back a moment. I showed this to Tony when I realized it was from constant right ascension. And he said, yeah, great, but that only takes up about 5 millimeters. We can't see what's going on. We need an enlargement. With this technology, getting an enlargement is simple. You run the chart paper faster under the pen and it all gets spread out. The snag is I couldn't run at that speed of chart paper all the time because it would get through the roll of chart paper in 20 minutes. And guess who would have to live at the observatory putting a fresh roll of paper in every 20 minutes? So the next best idea is the grad student goes out to the observatory shortly before this is due to appear, switches to high speed, and then when it's over, switch back to the normal speed. And I did that for a month, and the thing, whatever it was, had disappeared, and I made high-speed recordings of receiver noise. And my supervisor was furious. It's a flare star. It's been and gone and done it, and you've missed it. Grad students may have discovered that it's always the grad student's fault. But finally, after a month, I got it, and this is what came in. The bottom signal, bottom trace is 1 second time pips, and the upper trace is what came in. And in the center, you can see the regular pattern of pulses. You can see some off to left, and they're in phase. And going to the right, it goes quiet for a bit, and then there's another few pulses, low-level ones, also in phase. It keeps constant period. It keeps phase. And the period is about 1 1/3 seconds. Now, you will see that it is labeled LGM1. That label was added much later. I wonder if you can tell why. We did come to nickname these things Little Green Men, and they were ultimately numbered LGM 1, 2, 3, and 4. But with the first one, you don't call it 1 until you've got some more, until you've got a second or a third. And then you go back and relabel the first one number 1. So that label is clearly added much later. And it's in Tony, my supervisor's, handwriting as well. Now, Tony didn't believe me when I told him this is what I had recorded, and he came out the next day and stood looking over my shoulder. Scary point. This thing's been absent for a month. It appeared yesterday. Will it appear 2 days in a row? It did. He saw it with his own eyes, and he started to believe it. And we checked that the period was the same as on the previous day. So the thing, whatever it was not getting tired and slowing. It was keeping up its beat. Tony thought it might be interference, but it keeps sidereal time. The only people who keep sidereal time are astronomers. So we worried that maybe it was interference from another telescope or other astronomers in Cambridge, but we couldn't get that one sussed out. Tony assumed that I had wired the radio telescope up wrong and it was somehow my fault. But we got a colleague, Paul Scott and Robin Collins, who also had a separate radio telescope at the same frequency on the site with its own receivers. And it managed to pick up the signal itself. That was a huge relief to me. It meant I had not wired the radio telescope up wrong. But as we kept observing it, we could see it kept the same period, which meant it had to have large energy reserves. But the pulses are quite steep, so it has to be small. So it has to be big and it has to be small. We sharpened up that one ultimately. It has to be big in terms of mass, and it has to be small in terms of size. We still couldn't make sense of it at that stage, but that was one of the bits of information we extracted. John Pilkington, a postdoc associated with the group, managed to get an estimate of the dispersion, and with a lot of trial and error, showed it was about 200 light years away. So it's within the Milky Way, but it's beyond the solar system. Tony began to wonder if it was aliens, little green men. And he argued that if it was little green men, they would probably live on a planet that went around their sun, and therefore we might see Doppler shifts in the pulse period as they went around their sun. So Jocelyn kept faithfully observing this thing every day, and we looked for Doppler shifts. And we found a Doppler shift, but that was the Doppler shift due to the Earth moving round the sun. So we proved that the Earth went round the sun, but we weren't proving much else at that point. And just before Christmas, it's now about a month since I got the first pulse signal. Just before Christmas, I go to see Tony about something in his office, and the door is shut, which is a bit unusual. I knock, Tony says, "Come in," put my head round the door. "Ah, Jocelyn, come in," and shut the door. So I went in and shut the door. And there was a meeting going on that I think I should have been part of from the beginning. There was Martin Ryle, the head of the group. There was John Shakeshaft, who was a senior editor of one of the journals, Monthly Notices. And they were having a discussion about how on earth we publish this thing. We've only got one of them. We're beginning to run out of clever tests to do. And we really ought to publish. But how do you publish when there's only one? Nobody will believe you. We didn't resolve the issue that evening. I went home for some supper, came back in after supper to do some more of the chart analysis. And I'm busy analysing chart, the bit of the sky that's opposite Cassiopeia A. Now, you're blessed with Southern Hemisphere, so you're not troubled by Cassiopeia A. But Cassiopeia A is one of the very strongest radio sources in the sky. So strong that my telescope could see it through the back of the telescope. And just at that bit of sky where Cassiopeia A through the back of the telescope was making a real mess, I suddenly noticed a funny little squiggle, rather like that first one. They lock the laboratory at 10 o'clock at night. Students do not have keys. They can be locked in or locked out, and it is 5 minutes to 10 o'clock. I pull out the box that covers that declination, get out other charts, throw them out. Most of the data was repped by Cassiopeia A through the back of the telescope, but on 2 or 3 other occasions, indeed, I could see some hint of one of these funny little signals. Piled the charts on my desk and rushed out, the janitor closing the doors behind me, locking up. That piece of sky is due to transit at about 2 o'clock in the morning. I need to be out there. It's December the 21st. It's winter time in the Northern Hemisphere, and it was very, very cold. When I got out there, the telescope was not working properly because of the cold. I cursed it, I kicked things, I breathed on the receivers. I got it to work on the right setting for 5 minutes. It was the right 5 minutes, and in came another pulsed signal. The first one pulsed at a period of 1 1/3 seconds. This one pulsed at a period of 1.2 seconds. It's clearly of the same family. And it's not little green men. There aren't two lots. I went away home for Christmas with my boyfriend. We announced our engagement. I came back in January. Tony had kindly kept the survey running, which means he put paper in the chart recorder, ink in the inkwells, and piled the charts on my desk. When I get back, he's in a meeting, but there's a big pile of charts on my desk, rolls of chart paper, and I get down to doing some data analysis. And I'm busy working through these meters of chart paper and come across one of these squiggly signals. Oh yeah, which one's that? It's not either. It's not either. It's a third one. Okay, there's only about a meter of this roll of paper left. I'll finish it and I'll come back and do this. And I work on, and nearly at the end of the paper, there's one of these squiggles. I think, what? Another one? Two of them? About a meter apart? At that moment, Tony appears and stands at the end of the desk. Look, Tony, look, two. Oh, Happy New Year, Tony. Thank you for keeping the survey running. Look at this. Huh. How many more have you missed? Go back through all your old records. So I did go back through all my old records, several miles of it, several kilometers of it. I did not find any more, and we confirmed those two over the next few weeks. So we now had 4. We pushed ahead with the paper on the first one, and then there was a second paper for numbers 2, 3, and 4. So, pulsars today, having taken far too long describing that, sorry folks. Pulsars today, well, we believe that they have a strong offset magnetic field, as you can see in the right-hand diagram, that somehow, with a bit of hand waving, some people understand it, this magnetic field and the spin forms a beam of radio waves that come out of the cone area at the poles and swing around as the star spins. And when that beam shines in our face, we see a pulse. The other beam we do not normally see. There's just 1 or 2 pulsars where we see both beams. Of course, there will be many pulsars where we don't see any beam because of the way the beam is inclined. It does not shine on the Earth. So we now know they're very small, very dense, neutron-rich stars, and they're known as neutron stars. Because they're small and dense, they have very strong gravitational fields. They also have extremely strong electric and magnetic fields, and they're rapidly spinning. And they're probably formed in a supernova explosion. The famous supernova, the one in the Magellanic Cloud, for a long time, supernova 1987A, for a long time we couldn't find any pulsation from that. We thought there must be a neutron star there. Well, we still haven't found a pulsation from it, but interesting, the ALMA telescope, which is a millimeter wave telescope, studying hot gas and dust in the Large Magellanic Cloud, has found a hot spot exactly where that neutron star should be. So it looks as if we have at last found that neutron star, even if we don't see it pulsing. We'll see if the audio file works. It may not. So that's what a pulsar sounds like, as picked up by a radio telescope. Pulsars are primarily seen in the radio, but also in X-rays and gamma rays. We now have about 3,000 known. About 20 of them can be seen in the optical with difficulty, about 100 in X-rays, and a surprisingly large number, about 200 in gamma rays. Of the 3,000, about 10% are in binaries, and one is a pulsar-pulsar binary. There's also one in a triple system and a few with planets. The total number in the galaxy is debated. The number I'm giving here is 10 to the 5 in the galaxy. Crab Nebula is the source of a famous pulsar. Before the pulsar was discovered, there was a big problem about why this nebula kept shining. Indeed, Jeff Burbidge said there's two kinds of astrophysics, the study of the Crab Nebula and the study of everything else. It was such a big problem. Well, we then found the pulsar in the middle of the Crab, and that is basically what's keeping the nebula shining. The synchrotron radiation energizes the nebula. It's also one that you can see in the optical, which is interesting. Indeed, you can see it at many, many frequencies. It's quite a fast one as well. And it was the first pulsar for which we managed to measure the pulsar derivative, dp by dt. And that solved the question of whether pulsar was an oscillating object or a rotating object. As an oscillating object ages, its period gets faster. It kind of quivers. Amplitude gets smaller, but the period gets faster, and then it stops. Whereas a rotating object, as it ages, the period gets longer. And with this pulsar, they managed to show that the period was getting longer. So pulsars are rotating objects, not vibrating objects. So they're a little bit more massive than the sun. They have a radius of about 10 kilometers, so their density is huge, comparable with the density of the nucleus of the atom. Their structure is not yet fully solved. The solid state physics is challenging, but we know they are rich in neutrons, so they're also known as neutron stars. A thimbleful of neutron star material has the same mass as the population of the Earth, which means they also have a strong surface gravity, they have tidal effects, gradients of gravity, and of course they have very condensed matter physics. The strong gravity has some interesting effects. It bends light. So if you were on the surface of one of these stars, you could see 20 or 30 degrees over the horizon. You could see about half the star without moving. The gravity also redshifts light. So if there were little green men on one of these stars, they would look to us like little red men. And of course, gravity also affects clocks. So there the clock would do one tick every 2 seconds, not a tick every second. There's also a very strong gradient of gravity. So if you were to go visit one of these stars, your body would get stretched out by the gradient of gravity, and then it would start ripping your body apart. So don't go visit a pulsar. They have apparently very strong magnetic fields, about 10 to the 8 Tesla, and voltage drops of about 10 to the 9 volts per centimeter. So the electromagnetic sources are about 100 billion times the gravitational. The physics of these things is very extreme. Once you get one of these things spinning, it keeps spinning. So they are good timekeepers. They're good to about 1 part in 10 to the 16. Or put differently, the period of a typical pulsar has increased by about 1 second since the age of the dinosaurs. And so nature has given us a whole lot of very accurate clocks dotted throughout the galaxy. and we're able to use them to test Einstein's theories. I have to say Einstein's theories are testing very well so far. Magnetars. There are not many magnetars. It turns out they're peculiar pulsars, erratic pulsars, probably. The current understanding of what a magnetar is it's highly magnetized. Its magnetic field is even bigger than of a pulsar. It does pulse a bit erratically. It tends to be slow as pulsars go, and it can rapidly speed up or rapidly slow down. We believe they're formed in supernovae, but 10% of the supernovae that would give a pulsar actually give a magnetar. But they're very short-lived, probably only 10,000 years. If they are that short-lived, there must be a lot of dead magnetars in the galaxy, probably several billion. They produce short X-ray and gamma-ray flares, and they're suspected to be due to starquakes. The flares last about 1/10 of a second, and probably powered by the decay of the magnetic field. And each of those flares has a luminosity like 10 to the 5 years of solar luminosity. And yet we have a few dozen known, not many. Another fields, probably not related, but discovered by the pulsar people, are fast radio bursts. You will have seen spectra, optical spectra. You know that it's because light of different frequencies travels at different speeds through the glass or the raindrop or whatever. There are similar effects in radio. If a radio wave comes past free electrons, then the lower frequencies get slowed up more than the higher frequencies. And we came across this initially in a terrestrial context, whistlers. I'm going to see if this bit of audio works. You're going to hear a lot of static crackle. We're working at about 1 megahertz, 2 megahertz, so it's quite low frequency. But then in amongst all the static, there's suddenly this descending whistle. Let's see if it works. Where's my cursor? There we go. So that lovely descending whistle is in this case made by a lightning stroke on the opposite side of the Earth. Lightning stroke generates a radio wave of many frequencies, quite broadband, and that radio wave travels around to us following the magnetic field loops. And as it travels, it passes free electrons. The high frequencies get here first and the low frequencies later. And you can actually tell how far it's come by how spread out the high frequencies and the low frequencies are. On this graph, you can see a couple of vertical bars. There's one there and one there, either side of the descending whistle. These are not dispersed. All the frequencies arrive at the same time. So those radio signals have not gone far. They have not been past many electrons. Those are locally generated radio interference signals. And that's important when you're studying pulsars. Pulsar astronomers regularly make plots like this. There's a pulse here in amongst a certain amount of noise. We can see this spectrum against time. We see this descending curve. This tells us that this signal has come some distance and is not locally generated. It's a pulsar. Similarly, for this second one, where the signal to noise is much better, there's this descending curve. And the rate at which this curve drops is a measure of how many electrons it has been past and therefore how far away it is, because we can make an estimate of the electron density in the galaxy. But pulsar astronomers always check and do this kind of plot. They check the dispersion to make sure they've got something out in the galaxy and not a locally generated radio pulse. So here's another very nice example, a very, very strong, clean pulse. And here's its dispersion curve. But if you work out how many electrons you need to get this dispersion, it's rather high dispersion. It needs a lot of electrons. More electrons than there are in the galaxy in that direction. So it's beyond the galaxy in that direction. Interesting. When this burst pulse was discovered and they realized that such a large number of electrons were needed and it was extragalactic, they didn't really know what to do about it. They didn't feel they could really publish it. They needed some more repeats. But there weren't any repeats, and there was no record of anything previously from that direction. And there wasn't any optical, and there wasn't any infrared, and there wasn't any X-ray. Finally, they did publish it, and for a long time, well, 5 or 6 years, people were unsure whether to believe it or not. And then they started finding some more. So this is a sample of fast radio bursts, a fairly miscellaneous sample. They're all short and bright. To date, about 3,000 have been seen. They all have high dispersion, which means they're outside our galaxy. They're probably at redshifts between 0.5 and 1. A few of them have been seen to repeat. And for a while, the Australians were picking up something else. Looked a bit like one of these bursts, but wasn't exactly, and seemed to come from all over the sky. And they couldn't work out what these new kinds of bursts were. Until a graduate student, bless them, decided to plot the time of arrival of these curious bursts against local time. And there was a strong peak between 12 noon and 1 p.m, lunchtime. There was a microwave oven in the staff room at the observatory, but they knew it was leak tight because they had tested it and tested it. You don't want interference from your microwave oven if you're a radio astronomy observatory. So they knew it didn't leak. And then somebody had a thought. Suppose people are stopping the microwave oven by opening the door. Might that make a sort of burst? And so they tested that and found that was the case. I'm telling this story because until then, I stopped my microwave oven by opening the door, not by pressing the stop button. So I was giving myself a short burst of microwaves in the chest every time I did that. Maybe some of you do that as well. Don't. It's not healthy. Use the stop button, please. So having solved that some of the bursts were the microwave oven in the staff room at Parkes Observatory, that still left a lot of bursts and more being discovered. ASCAP, the Australian precursor of the square kilometre array, has managed to position some of these, about half a dozen of them. And this is a recently published paper showing the location of these bursts. The blue, green, yellow splodges are radio galaxies. The red X marks the center of the galaxy, and where you can see it in this diagram, the white circle or white ellipse, like here, 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 marks the position that the fast radio burst came from. And, well, it's somewhere in a massive galaxy. It's an improvement, but not really a great improvement yet. So where are we now? Well, we think there are two kinds. There are the minority that repeat and all the others, which might be from a catastrophic event. They're found in the outer parts of massive galaxies. Yeah, okay, so, And do they emit at other wavelengths? This is debated at the moment. Some people think they've picked up maybe X-rays or gamma rays, but maybe not. I think we need to wait and see on that one. These undoubtedly are fascinating objects. They're picked up by the pulsar astronomers, and that's why I've included them in this talk. I'm not clear that they are anything to do with neutron stars or pulsars, but they do give super pulses. Thank you for your interest and your attention, and I'm sorry to have taken rather long. Thank you.
Thank you, Professor Jocelyn. So please don't apologize for taking our time. On the contrary, people were thrilled to see your presentation, and people were really moved by the story of the discovery of the first pulsar. So thank you for that. It was a brilliant talk, and it was beautiful how you walked us through with so much detail through the moment in which one of the greatest discoveries in astronomy happened. So thank you again for your contributions to astronomy, and thank you again for sharing your time with us to tell your the story of your brilliant career and brilliant discoveries. So you see that on the screen. So people are very honored to watch your seminar. You can see here, for instance, that you are a great inspiration to women to pursue a career in astronomy. So that's fantastic, and it's a great opportunity for us to have you giving this talk to us. So we have a few, and I should tell you that you broke the record in our seminar. So with the most the highest number of viewers so far. So that's really impressive, and I'm sharing this with you to show you how much people appreciate your work.
How big is the audience? Was the audience?
Yeah, so we have a few questions here in the chat. So I will show you here on the screen, and I'll also tell you. So this is a two-part question from Elio. So he wants to know what an undergraduate course could do to better teach radio astronomy to its young students, and then if a homemade radio antenna can give enough knowledge and prepare them for using professional tools.
With a homemade radio telescope, you can do interesting things, observing the hydrogen line in our galaxy in different directions, and seeing it redshifted different amounts in different directions because of the rotation of the galaxy. So you can get the rotation of the galaxy by studying the hydrogen line. That's one of the easiest things to do, and also teaches quite a bit of galactic astronomy as well.
And do you think that would be useful, for instance, in undergraduate course for students to get in touch with radio astronomy?
I think it's not if it's at the expense of physics, because you need the basic physics to be an physicist. But if there is time to spare, then it can be huge fun. Also to a great interest, also to be learning some radio astronomy or all the wavelengths of astronomy, to be honest. I think they're all important.
Great. So I'm scanning through the comments here. Lots of comments saying amazing talk and inspiring history. So thanks again for that. Okay, we have another question here. This is from Marco. So what could you say about future breakthroughs in astrophysics regarding pulsars now with the quite new gravitational wave astronomy?
Yeah, gravitational wave astronomy is huge fun too, isn't it?
Yeah.
I think what's going to be particularly interesting is watching a supernova where a pulsar forms with the gravitation. I think that will be, it'll be hard to catch, but that will be really very good. But the gravitational radiation results are complementing a lot of the other electromagnetic results, so that's fun. And yes, I think gravitational wave astronomy is very well worth watching. It deals in energetic events like supernovae and pulsars and mergers.
Okay, thanks. So we have another question here from Iana. So she's thanking you for the excellent talk. So she was intrigued by the end of the lives of a pulsar and what are the remains of a dead magnetar.
Right. I think a dead pulsar and a dead magnetar are rather similar. What happens is they spin more and more slowly, they grind to a halt as they lose energy. And when the spin rate gets sufficiently slow, there doesn't seem to be the energy to generate the radio beam. And so it becomes a dead pulsar or a dead magnetar. And there must be a number of dead pulsars and a lot of dead magnetars. So they remain as neutron stars, but probably not very visible and not very active. The one exception being is if they are in a binary system, in a close binary, because the strong gravitational field of the neutron star will pull material off the binary companion onto the neutron star, and that can spin the neutron star up. And it could spin it up so much it becomes a pulsar again, and then dies again.
Wow. So we have the pulsars come back. Some pulsars may come back to life.
Some may, yes, if they're in binaries. Yeah.
That's very interesting. And besides coming back to life, is there, let's say that the pulsar or the magnetar is dead. So is there a way to find these dead pulsars or magnetars?
Only by falling into it.
Okay. So not a very good hypothesis, right? Okay. So moving on to the next comment and question. So we have Karin, and she says that one of her first undergraduate projects was on pulsars, and at the time the search for lower than 1 millisecond pulsar was still on. So what is the fastest pulsar to date, and what sets the limit?
I think we're still looking for pulsars that fast, and I don't think we've found them, to be honest. One of the things you need to think about is the centrifugal effects. If it goes too fast, in spite of the strong gravity, would it disintegrate?
Okay, thanks. So just so you see, the people are excited. People wanted you to talk for 3 hours. So yeah, so people are very excited with the information that you, yeah. Yeah, and that's important to tell you guys. So Professor Jocelyn is on Europe, so it's much later for her, and she was very very nice to keep our current time for the seminar. So thank you very much for that too. And we have another question from Karin. So can you tell us a little bit about the status of efforts using Pulsar to detect gravitational waves, meaning Pulsar timing array?
Yeah, there are several. No, I start that. You know probably about LIGO and the work that gravitational wave detectors has been doing. There's other ways of studying other frequencies of gravitational wave, and a pulsar timing array covers a different frequency range, a rather higher frequency. Have I got that the right way around? Lower. They're different. I won't try and do it in my head. The idea is that when a gravitational wave comes past, the pulsars move, rock in the wave. And as they rock, you may see Doppler shifts on the pulsar period. Now, there are lots of things that could cause a pulsar period to look like that. So you have a whole array of pulsars and see if first the distant one rocks and then the nearby one rocks and so on. There are tests like that that you can do. A number of pulsar astronomers have been working on this for quite a few years. They don't have a detection yet, but I think it can't be too far away because there is a pulsar timing array, largely in North America, working on this.
Okay, thank you. So moving on, so we have this, so Luigi makes a comment about using, he says that a fraction of the fast radio bursts could be associated with gravitational waves. So with the current radio telescopes available, how can we precisely identify the sky position of this source?
Yeah, so far well, it's more likely to be the bursts, yes, than the pulsars. So far, they haven't seen any radio burst coincident with a gravitational wave, or even approximately coincident. The issue, well, it's difficult with bursts because you don't know where the next one is coming from and you don't know when. We are gradually developing better use of telescopes to pick up more bursts. Meanwhile, the gravitational wave people are also improving their telescopes, but they really struggle with stellar mass things. They're doing quite well with things that are 20, 30 times the mass of the sun, but really struggle if it's only 2 times the mass of the sun. They don't have the sensitivity. So at the moment, it's the gravitational wave detectors that need to get more sensitive for the gravitational wave and the radio wave telescopes to work together in this way.
Okay, thank you. So moving on to the last few questions, because it's late for you and we are a little bit over an hour. So a question for the future here. So what do you think will happen within the next few years in the research about pulsars and magnetars?
They are using pulsars to test theories of gravity, and I think there could be developments there. We have a pulsar in a triple system, and this is allowing us to check out other aspects of Einstein's theories. So far, Einstein's theories have checked out pretty well, really, really well. And the problem is how to beat down the experimental errors to test them even more rigorously. But certainly using them to test theories of gravity, Einstein's theory of general relativity, are, I think, some of the areas with the greatest impact.
Okay, thank you. So 2 more questions, okay?
Yeah, sure.
Okay, so this is an interesting comment. So Ariel may have missed some part, but he's curious about how did you find out that you were looking at neutron stars actually?
Yes, I didn't explain that, so you didn't miss it. I just when we first found these things, there were 2 possible options. One was rotating neutron stars. The other was oscillating white dwarfs, that they would oscillate at some sort of natural period. They would launch shocks up through their atmosphere, and somehow that would turn into a set of pulses, a string of pulses. Now, there's actually quite a neat test you can do to separate these two, because if you have something oscillating, as it gets tired, it quivers and stops. And that quiver is small amplitude, it is high frequency. Whereas if you have something rotating, as it stops, it slows and its frequency gets lower. So what you need to measure is the period derivative, dp by dt. How is the period changing as this thing ages? We were able to do it first with the pulsar in the Crab Nebula, and we found that the period was getting slower with time, which means it's a rotating object. If it had been a vibrating object, it would have got faster with time. And Tony had a model of a white dwarf with vibrations and launching shocks up through the atmosphere, a bit like solar storms. So he had that model, but it had to be the neutron star because we saw that the period was getting longer. dp by dt is positive.
Very interesting. Thank you very much for this explanation. Okay, so moving on to the next, it's some people ask this question, so I'll merge them. So I'll show this one from Maria Clara. So she asks you, how did you deal with the difficult times in your career, especially being a young woman in astronomy, making a huge discovery, and some other people asked if you could provide any advice for young women in astronomy. So can you please comment on your personal experience, and based on this, what would you give? What advices would you give to young women in astronomy?
I was lucky in that I knew before I left high school that I wanted to be a radio astronomer. And that helped because I was the only female in the undergraduate physics class. And at that time, at that university, this wasn't Cambridge, it was the tradition that when a woman entered the lecture hall, all the guys whistled, catcalled, banged their desk, stamped their feet, made as much noise as possible. And I had to face this on my own, but knew I had to get a physics degree. And then I got to do radio astronomy. I got engaged to be married between discovering Pulsars 2 and 3. And I got married between submitting my thesis and having the Viva exam on the thesis. And that resulted in a period where I was married to a man who he worked in local government, and he had to move to another region quite regularly. And then there was a child. So I was working part-time. And when we moved to a new area, I would write to the nearest astronomy place and say, might you have a part-time job for me? I'm keen to keep working. I have the following experience. And because I had the discovery of pulsars behind me, directors of observatories usually could find a little bit of money for me to work part-time. But I went from radio astronomy to gamma ray astronomy, then to X-ray astronomy, then to infrared and millimeter. And then the child was going to university, the marriage broke up, and I was able then to go for jobs that suited me rather than suited the family. And it's a crazy career, but it has been really interesting. I've been quite lucky, and of course I've learned a lot through working at all these different wavelengths. So my advice is, be clear if you can about what you want to do. Do you really want to do astronomy? If so, and if you get married, if you have children, if you have to work part-time, be prepared to compromise. You may well have to change wavelength. I did not always have a research job. Sometimes it was a service job, but it keeps you in the field. It keeps you in touch with what's happening. You make new colleagues. You learn new techniques. So your career may have to be quite a lot of compromise, but you'll probably end up more broadly educated than your male colleagues. And that's not bad.
Thank you very much for, yeah, that's exactly one comment that's appearing on the screen. So thank you very much for sharing your history, your story, and telling us about the amazing work you're involved with. And I would just like to let you know that lots of comments here saying that you're an inspiration for all undergrad and graduate students, especially with the groundbreaking discovery. And I would like to end this broadcast showing you that you inspired and you continue to inspire lots of young students. So you can see that people want to be astrophysicists because of you. So that's a brilliant career with great contributions, and it was really a huge honor and pleasure for our institute to host you, and for me personally to host your talk. So thank you very much for sharing your time with us, and it was a brilliant talk. If you want to say any final words.
Just to say thank you for the invitation and everybody's patience in listening. And thank you particularly for all the help with getting the technicalities sorted and getting the PowerPoint up. Thank you very much indeed for the invitation. I've really enjoyed it.
Yeah, and we are very happy. And if possible in the future, we hope to have an opportunity to have you with us here in person. Let's hope that we can do that in the near future. So right now, I'll end the broadcast, but you can still be on the StreamYard, so we can end the broadcast later. I'll just end the broadcast on YouTube, okay? I'll just say a few words. So everyone, I'll just like to thank you all for the audience. It was one of the greatest audience, the greatest audience we had so far in our seminars. So thank you very much for that. I'm sharing the link for the next seminars, and they are on our website. So please follow our social media and our channel on YouTube to get reminders for the next seminars. We have a very nice set of speakers ready for the semester. So thank you very much, and see you all next week. Have a great afternoon.